Today, we're going to basically redo what we did over the last few lectures. We spent the last several lectures learning how to compute decay rates and cross-sections. So first, by an analogy with the classical definitions of decay rates and cross-sections, we related decay rates and cross-sections to scattering amplitudes or matrix elements. Then, using the LSE reduction formula, we related those matrix elements to Green's functions in the interacting theory. And by going to the interaction picture, could relate those Green's functions to Green's functions in a free theory, or time-ordered expectation values of interaction picture fields. Which we can then compute using Wick's theorem by relating this to the Feynman propagator. And so in this expression, these are Heisenberg picture fields. Over here, these are interaction picture fields, what I labeled as phi sub 0 of x1 yesterday. But from now on, I'm just going to drop the most part, going to drop the subscript zeros to indicate the free, that in the last lecture indicated the free fields or interaction picture fields. And it should be clear from context whether we're dealing with a Heisenberg picture field or a interaction picture field. Interaction picture fields will always be in expressions involving the free vacuum. Heisenberg picture fields will be in expressions that involve the interacting vacuum. And so this is what we've done. It took us about 3 lectures to learn how to compute these things. And today we're going to basically learn a faster graphical way to compute either first the Green's function. So the first part of the lecture we'll see how to go back and forth between the Feynman propagator and the Green's function. And then we'll go one more step and see how to go back and forth between the matrix element and the Feynman propagator. So we'll do both of these things today using Feynman diagrams. So we'll retrace our steps and basically go through this story again and see how to represent things in terms of Feynman diagrams. So that's where we're going. And before we do that, I'd just like to thank you for the feedback on the survey. And there's one comment that was more of a question that I'd like to address. So there's one question on the survey that was asking about the different normalizations that you see in different texts for the ladder operators. So we've assumed that our creation operators create or our equivalently, our commutation relations involve a factor of 2e, which is not always there in every text. Different texts sometimes put the 2e's in different spots. The question was whether these different conventions are the same or whether we'll get the same results. And the answer is yes, we always get the same results regardless of how we choose our normalization. I've chosen the relativistic normalization because the 2e's always go in the measure. And you'll always get the same result for the energy. If you act with the normal ordered Hamiltonian on any state, those results will be independent. Or if you compute a matrix element or a cross-section, those results will not depend on a choice of normalization. Some of the intermediate results will have factors of 2e in different places. But those are equivalent. Okay. So that was a side note. So this is where we're going today. We're going to first see how to go compute the Green's function using pictures, and then see how to compute the matrix element using pictures. And the way we're going to do this is we're first looking at an example. So start by looking at how we can represent this free Green's function using diagrams. And then we'll look at how we can represent this interacting Green's function using diagrams. And through those examples, we'll come up with, or I'll motivate a set of rules for which diagrams, which pictures you should draw in order to compute this Green's function, and how to associate analytic expressions with each of the diagrams. So that's what we're going to do. So we'll first do that for the Green's functions, and then we'll use our results here to motivate a set of Feynman rules, which are rules for which diagrams we should draw to compute the matrix element and how to associate analytic expressions with those diagrams. And when we're in position space, the basic idea that we're going to use to decide which diagram to draw is we're going to represent each space-time point by a point, and each propagator, each Feynman propagator, by a line. So if we look at the expression we concluded yesterday's lecture with, so we computed the free Green's function here, and what we found was this. Using Wick's theorem, we found that this was the sum of products of Feynman propagators. And just as a reminder for the notation, so phi sub 1 means phi of x1. So this is this field is evaluated at the space-time point x1, and these are Feynman propagators from x1 to x2. So using that idea, so we've got 4 space-time points here. So I can draw the 4 space-time points. I'll label them 1, 2, 3, 4. And in this first term, we have a propagator from 1 to 2 and a propagator from 3 to 4. So this will be the Feynman diagram I'll use to represent this term. And then we have 2 other terms. And I'm going to put the space-time points in the same relative locations as I did in the first diagram. I suggest always doing that. It's easier to tell if you've drawn the correct diagrams that way. And so here, it's the same, except we have a propagator from 1 to 3. So I draw a line from 1 to 3 and from 2 to 4. And in our third diagram, we have a propagator from 1 to 4 and a propagator from 2 to 3. And so there's no space-time point in the middle where these lines meet. So I'm drawing this line jumping, or you can think about it as going under or over this other line. They don't meet. And I'm referring to these 2 lines and 4 points as a single diagram, even though it's not connected. So this is what I mean by one diagram, because it represents one term in our expression. Okay. And as I mentioned before, it's the best practice to keep the points to the same point. Keep the space-time points in the same location on each diagram. Okay, so that's just a very simple example of what we're going to try to do. It's not very difficult to do, draw the diagrams for the free time-ordered products of free fields, back in expectation values of those products. because by Wick's theorem, we always just have a product of propagators. So there's never going to be any diagrams that are more complicated than this. Each point will be connected to exactly one other point by one line. What's interesting are how to draw Feynman diagrams for the Green's functions, these interacting Green's functions. So let's compute an example and see if we can then, from that example, motivate or guess what the Feynman rules should be in general. Okay. So the simplest Green's function we can look at is a 2-point Green's function. And we saw yesterday that we can compute this Green's function by going to the interaction picture and using Dyson's formula. And the result is we've got the time-ordered product of phi1, phi2 times its exponential of I times the integral of the interaction Lagrangian. And normalized, so we have just the time-ordered exponential in the denominator. And for concreteness, let's assume that the interaction Lagrangian is minus lambda over 4 factorial phi to the 4. In my notes, I called this y, so I'm going to change this from an x to a y. But it doesn't really matter. Okay, so we'll look at the numerator and denominator separately. Let's look at the numerator first, and we'll come back later to the denominator. So the numerator here, if we want to compute this, we have to do perturbation theory, and that means expanding the exponential. So what we've got here is our first term. From expanding the exponential, we just get a 1. So that's just time-ordered product of phi1 and phi2. Our next term is going to be time-ordered product of phi1, phi2 times minus I lambda over 4 factorial integral d4y of phi y to the 4th. And we could go to higher order if we'd like, but stop here. Okay, so this first term is easy to draw a Feynman diagram for. There's basically nothing new compared to our previous example. So this term here is just equal to delta 1, 2, which we can represent by a Feynman diagram like this, with 2 space-time points, 1 propagator. Okay. This term is more interesting. So we can evaluate this term by using Wick's theorem. So Wick's theorem says that the time-ordered product is the normal ordered product of all possible contractions. And if we take a vacuum expectation value, only completely contracted combinations will survive. So we need to figure out what are the possible ways we can contract this combination of fields. And there are 2 ways we can do that. So the 2 ways we can do that are, so we've got here phi1, phi2, phi y, phi y, phi y, phi y. So one possibility is we can contract phi1 with phi2. And then we can contract the phi y's with themselves. And so we'll need to count, there's several possible ways we can do that. So one way is we can contract contract the first phi y with any of the other three phi y's. So there's three possible choices here for the first contraction between a phi y and another phi y. And then once we make that choice, we're forced to contract the last two together. So there are three contractions like this. Another possibility is instead of contracting phi 1 with phi 2, we can contract phi 1 with one of the phi y's. There are four possible phi y's to choose from. So there are 4 times 3, because there's 3 possible ways to contract phi 2 with one of the remaining phi y's. And then we're forced to contract the last two. Okay, so this term gives us two types of terms. And so what we have is this term by Wick's theorem, y, is 3 times minus I lambda over 4 factorial times the contractions become Feynman propagators. So we get, for the first type of term, we have a delta 1, 2, integral d4y, delta yy, delta yy. And we can represent, well, let me write the other term first. Then we have 12 minus I lambda over 4 factorial, integral d4y, delta 1y, delta 2y, delta yy. So this term will give rise to two Feynman diagrams. And so if we want to represent this using Feynman diagrams, our first term has the points 1 and 2 connected by propagators, so we draw a line between them. We also have an internal point, y, and there are two propagators from y to y. So we need to draw two lines starting and ending at y. So this is the first term. And the second term, again, we have the points 1, 2, and y. My suggestion here was maybe should have been more specific. At least keep the external points in the same place. The internal points, sometimes your diagrams will look much cleaner if you move them around. So I'm going to do that here. And so I'm going to, I've kept 1 and 2 in the same relative positions, but now I moved y in between, and we've got a propagator from 1 to y, from 2 to y, and another one from y to y. So this diagram represents this term. Okay. So we'll come back to the denominator, but this example is already enough to guess most of the Feynman rules. I'll go on this board. Before I write these down, are there any questions on this? So the denominator is going to come back and modify which diagrams we consider. So I'm just going to leave some space here to exclude some diagrams, and we'll come back to that. But we can already start to guess that the rules for which diagrams contribute and how to go backwards just from these examples. So first of all, diagrams to contribute to the endpoint function. This will be the sum of all diagrams with n external points. And the denominator is going to modify this, so I'll leave a blank here. We'll have to exclude some diagrams. But everything else will be unchanged. Okay, so this will be to be filled in later. So we can guess. So if we had more than 2 points here, we'd have more than 2 fields out front, and that means we'd have more than 2 external points. External points are the ones that are not integrated over. So that's our first attempt at which diagrams to contribute. So this will be modified. Everything else will not. Okay, so if we want to compute this, first we draw the relevant diagrams, and then we need to be able to associate an analytic expression with each diagram. And our first rule is for each line from x to y, we get a Feynman propagator from x to y. That's how we determine which diagrams to draw. The second rule is going to seem trivial, and it is for scalars, but I'm just writing it so that you don't forget it when you encounter particles with spin greater than 0 in Tibber's part of the course. And this is for each external point. We get a factor of 1. So I'm just writing this so that remember it when you come to particles with non-zero spin. Our third rule is for each vertex. So in our example, vertex, all of our vertices have 4 lines meeting. So we see that we got a factor of minus I lambda and an integral over the location of the vertex in these diagrams where we had vertices. We didn't have anything like that in this term, and we can imagine if we went to higher order, we'd have more coupling constants, more integrals, and we'd also have more an extra power of 5 to the 4th valued at the same space-time point, so we'd have an extra vertex. So for each vertex, we get a factor of minus I lambda times an integral over the location of the vertex. I'm not including the numerical factors. That will be accounted for in the next rule. So this specific form of the vertex rule, so which vertices are allowed and what factor to assign to them depends on our theory. So we have 4 lines meeting at the same point because we started out with a Lagrangian that had 4 powers of the field. So this example this rule is specific to phi-4 theory. So what would happen more generally? So we can imagine if our interaction Lagrangian contained a term that was like minus g over n1 factorial, n2 factorial, n3 factorial, verified to the n1, regular phi to the n2, psi to the n3. So 3 different fields, and you can imagine how to generalize it if you had more or only 2. Then you would get, well, you'd have n1 of this type of field meeting at a point with n2 of this type of field and n3 of this type of field. So we'd have a vertex that looks like this. And have different types of lines representing the different types of particles. So here we have n1 verify lines. We'd have n2 regular phi lines. And we'd have n3 psi lines, all meeting at the same point. We had this term in our interaction Lagrangian. Every time we went to higher order, we'd get an integral of this, all evaluated at the same space-time point. So we'd have that many fields all meeting at the same space-time point, C. And these factors of n1 factorial, n2 factorial, n3 factorial are just chosen to make the counting in the next rule work out. And this is the conventional way to normalize interaction terms. And so our last rule is divide by the symmetry factor. S. Okay, so using the first 3 rules, we can get everything right. We just saw these diagrams. We could reproduce these expressions apart from the overall numerical factors. And that's what this last rule is meant to take care of. And so the symmetry factor is defined to be the number of ways a diagram can be deformed so that it looks the same with the external points held fixed. This is important.
We have like different kind of field, 3 field, T-type field, so we have like T-type of lines. Imagine from one vertical.
Okay, so this last rule probably needs some examples to see how this works. And let's just check that we can reproduce these coefficients using this new way of the symmetry factor method. So we first came up with these coefficients by counting the number of Wick contractions, and that's entirely equivalent to using the symmetry factor. So the relationship is that 1 over the symmetry factor is equal to the number of Wick contractions divided by the factorials, whatever factorials are there in the Lagrangian. And the reason this method is easier than counting the number of Wick contractions is that in practice, most often the symmetry factor is a small number, 1 or 2. So with practice, computing the symmetry factor is easier than computing the Wick contractions. They're entirely equivalent. And I suggest if you're, for the first few times, you do it both ways just to make sure you're understanding them both properly. Okay. So let's look at this diagram first. And so this diagram has a symmetry factor of 2. One way we can deform this diagram so that it looks the same with the external points held fixed is we can switch the two ends of this propagator from y to y. So we can switch the two ends of this propagator, which means the symmetry factor is 2. So 1 over s is 1 over 2. And when we computed the number of Wick contractions, we found there were 12. And we had a 4 factorial from, that was the coefficient of lambda in our interaction Lagrangian. And in fact, 1/2 is equal to 12 over 4 factorial. So we get the same thing both ways. So this 2 comes from the exchange of the two ends of this line. Okay. Let's check. Let's look at the other one just to make sure that you understand how this works. So our other diagram was this diagram. And this diagram has a symmetry factor of 2. We can exchange the two ends of this upper line. We also have a factor of 2 from exchanging the two ends of the lower line. And we also get a factor of 2 from exchanging the upper line and the lower line. If we do all of those things, the diagram looks the same. And so 1 over s is 1 over 8, which is equal to 3 over 4 factorial. So again, it works. And so the types of symmetries we should be looking for are exchanging ends of lines, exchanging two lines or multiple lines. We can also have diagrams where we can exchange vertices. So sometimes we have several internal vertices that are, it doesn't matter how we label them, they have the same relationship to the external line, and we'll see some examples like that later. Are there any questions on this? Yes.
This rule works because we have defined the Lagrangian to be lambda over 4 factorial, but if we didn't put the 4 factorial, it will not.
Yes, this rule works as long as we always normalize our interaction terms in this way. So if we've got basically count the number of ways we can permute the fields in our interaction term. And it's essentially everywhere I've ever seen interaction terms written down, they're always normalized in this way.
Standard number of Wood contractions.
Oh, the factorials in the interaction Lagrangian. Okay. So those are our Feynman rules. We didn't consider the denominator. The denominator is going to have the effect of changing which diagrams we need to consider. We're going to end up throwing away some diagrams that are known as vacuum diagrams. And to see that, let's look at the denominator in our example. Okay, so our denominator in the same example is just the time-ordered exponential.
Sorry.
And we can expand this out. We get 1 time ordering of minus I lambda over 4 factorial. Our next order term is, I'm ordering, take that term and square it. And we could keep going if we wanted, but let's stop at second order. Okay, so we can represent each of these terms in terms of Feynman diagrams. So this first term is 1. There's no good way to represent it in terms of Feynman diagrams that I know of, so I'll just write it as 1. Our next term looks very similar to something we've seen before already. We have no external points, so the only thing we can do with these 4 fields is contract them among themselves. So we'll get a diagram that looks like this, which was part of one of the diagrams we saw before. And that's not an accident, and we'll come back to that in a few minutes. Okay, now this term, there are several possible diagrams we can get corresponding to the several ways we can Wick contract these fields. And, well, so the possibilities are I could Wick contract all of the y's among themselves and all of the z's among themselves. If I do that, I get a term that looks like this term squared. I could also contract 2 of the y's with 2 of the z's. And so if I do that, y and z, 2 fields contracted, there's 2 left over, 2 y's left over that have to be contracted among themselves, 2 z's left over that are contracted among themselves. We get a diagram like this. The last possibility is every y is contracted with 1 of the z's, in which case I'll have 4 lines from y to z. I can represent that by a diagram like this. So at second order, these are the diagrams. And so we've seen this figure 8 diagram 3 times already. It was in the numerator, in the first order term in the denominator, and it's here squared in the second order term. And it's not an accident that it showed up so many times. In fact, we can understand or guess what's going to happen to these vacuum diagrams by noting that these first 3 terms can be written as the exponential of this diagram. Exponential of the diagram, not of 8. Doesn't really help to draw it the other way. Then it looks like the exponential of infinity. This is the exponential of the diagram. So the exponential of the diagram is 1 plus this diagram plus a half of this diagram squared. And, well, if we're comparing this diagram, or this product of diagrams to this diagram, we've got this extra factor of a half that comes from expanding the exponential. But this is a single diagram, and it doesn't matter. This diagram has an extra symmetry from expanding the vertices. It doesn't matter which of these vertices I label as y and which is z. This is exactly the same diagram. I can exchange these because these are internal points that are integrated over. So this has an extra symmetry factor of 2 compared to this diagram squared. So this single diagram is equal to a half of this diagram squared. And so we get some of the terms just from exponentiating this diagram. And in fact, we can understand all of the terms in the denominator as the exponential of connected vacuum diagrams. And to see this, yes.
Why we don't have the 1/2 when we expand the exponential? Because of the t?
When we expand
Exponential?
yes, we should. It should be here. Yes. It should be here, but that's right. And this a half has the same origin as this a half if we want to compute it from the diagrams. There will be 3 ways to get a Wick contraction between the y fields that look like this. 3 ways to get a Wick contraction like that. In order to understand the overall coefficient using the symmetry factor method, we need to account for the symmetry between exchange of the vertices.
So at the end, this 1/2 disappears when we go from the first line to the second one?
Yes, that's right. There is no 1/2 in this. Was there another question back there? Okay. So the claim is that all terms in the denominator come from the exponential of connected vacuum diagrams. By a connected vacuum diagram, I just mean a diagram with no external points, like these. All these are internal points. Internal points are the ones that are integrated over. And by connected, I just mean that you can get from any point on the diagram to any other point by following some lines. And so we can write the denominator. So there's some set I'll call VI of connected vacuum diagrams. We've seen some examples. There's this diagram, this diagram, this diagram, and infinitely many others. And every term in the denominator, we can specify a term in the denominator by specifying how many of each of these diagrams are in that term. All the terms in the denominator contain no external points, so there'll just be some number of vacuum diagrams, some number of connected vacuum diagrams multiplied together. They have multiple copies of the same ones, but every term we can write that way. And so we can write the denominator as the sum over all sets of integers and I. And it's a product over I. We have multiple copies of the same connected vacuum diagram. We'll get an extra factor of ni factorial. Then we'll have vacuum diagram VI to the power ni. So what this is saying is that each term contains some number of each of the connected vacuum diagrams. It has an extra symmetry associated from exchanging the entire diagrams. And we can specify just some set of integers to specify how many of each one we have. We can write this in another way. We can write this as the product over I times the sum of ni factorial vi ni. So here we're just summing over all possible numbers of each of the vacuum diagrams. So we could have 0, 1, or 2 copy or more copies of this diagram, and the same for this diagram. And if we multiply each of those sums together, we'll get all the possibilities. But this here is nothing other, in the parentheses, is nothing other than the exponential of vi. Just the exponential of this diagram. The same reasoning we used here. And so it tells us the denominator is equal to the exponential of the sum of the vacuum diagrams, of the connected vacuum diagrams. And we saw at least one of these connected diagrams show up in the numerator. And that's not, again, not an accident. We can classify the terms in the numerator in a very similar way to what we've just done here. So for the numerator, each term in the numerator will contain a piece with two external points. So I'll call that part Ci. So for example, you could have a term like this. Could have a term like this, and there are other possibilities. We could have something like this, for instance. And these are connected diagrams with two external points. So we saw that when we expanded the numerator to first order, we had this diagram. We had this diagram with the first of the connected vacuum diagrams. And we had this diagram. In higher order, we'd have other connected two-point functions, two-point diagrams. And it would involve products with more of the vacuum diagrams. But every term in the numerator is going to consist of exactly one of these connected two-point diagrams and some number of vacuum diagrams. So in the same way as we did for the denominator, we can write the numerator as, so we need to specify which of the connected two-point diagrams we have. And again, we can have any possible set of vacuum diagrams. So we have one connected diagram with two external points and some number of diagrams, connected vacuum diagrams. And so the numerator can be written like this. Every single term is going to be of this form. It'll be, well, right, maybe I should write the Cj first. Cj times the product over I. So the Cj times some number of connected vacuum diagrams. And the Cj's completely factor out of the sum. So we can write this as the sum j of Cj times exactly what we had before. And this is just the exponential of the sum of the connected vacuum diagrams, which is the same as the denominator. And so this cancels out. So we have, if we are computing the Green's function, we want the ratio of these two things. And we see that we should just, we can just cancel off this exponential, the sum of vacuum diagrams. And so there's no reason to compute the vacuum diagrams if we're just interested in computing the Green's function. They cancel off. And so we can now correct our position space Feynman rules. And so Green's function is equal to the sum of all diagrams with n external points and no vacuum diagrams, because they cancel between the numerator and the denominator. Are there any questions on that? So this is how we can compute the Green's function using Feynman diagrams. This is something we're occasionally interested in its own right, and we'll study this properties of these Green's functions more in QFT2. But the object we'll be most interested in computing in this course will be the matrix element, which is defined in momentum space. So we'll need to develop a set of momentum space Feynman rules to compute. So our goal is to compute the matrix element using these diagrams. So we're going to, again, go through the same kind of thing, look at some examples to see if we can guess or at least motivate what the Feynman rules should look like. So the Feynman rules will tell us which diagrams to include and how to go backwards from the diagrams to the analytic expressions. Okay. And so remember, matrix element is related to the S matrix. We pull out the uninteresting part, the part where there's no scattering, and we also pull out a momentum conserving delta function. And then what we're left with is the matrix element. Okay, so in order to compute this matrix element, we need to use the LSE formula. We now know how to compute the Green's functions that appear on the right-hand side using Feynman diagrams. And so we'll use that result to see what Feynman diagrams we should draw and what expressions we should associate with them. And so the LSE formula tells us that FSI is, and we'll consider 2 to 2 scattering. Just for simplicity, not much of what we'll do will depend on that. The simplest interesting case. So we've got an integral, LSE formula, we've got an integral over the space-time position of each of our points. We're basically taking a Fourier transform. of our Green's function after we apply the Klein-Gordon operator to it, or Klein-Gordon operator for each particle. Okay, so this is our expression. So what we want to do is take our results for the Green's functions, apply Klein-Gordon operators to them, and then Fourier transform. And so we know how to compute this Green's function using Feynman diagrams, and at leading order, there are 3 Feynman diagrams that contribute to this. 3 we drew at the beginning of lecture. And when we're talking about scattering, it's useful to specify a direction of time in our Feynman diagram. So we've got 2 initial particles, 2 final particles. Sometimes time goes to the right, sometimes it goes up. Different people use different conventions. I'll try to label each of my diagrams. And so we've got three diagrams. They contribute to this. And so let's see what contribution these diagrams give to the matrix element or scattering amplitude. Based on the simplicity of these diagrams, you might expect that diagrams are not going to give us an interesting contribution. Doesn't look like there's scattering going on if we draw non-trivial scattering if we just look at these diagrams. But let's go through the exercise anyways to see how that shows up when we evaluate the right-hand side of the LSE reduction formula. Okay, so let's just pick one of these terms to look at and see what contribution it gives us. So let's look at this term. And our Feynman rules, position space Feynman rules tell that this is equal to delta 1, 3, delta 2, 4. And so we can already see just by looking at the LSE reduction formula and the explicit form of the contribution from this diagram that the contribution to the S matrix from this diagram is the product of 2 independent contributions, one from the x1, 3 and one from the x2, 4. We're just multiplying those things together. There's nothing in the LSE formula that would mix together x1 and x3 or x1 and x2 or x3 and x4. So we can just consider the 2 factors separately. And so let's look at what happens when we apply the Klein-Gordon operators and do the Fourier transform with just to this 1, 3 part of our Green's function. So we can define a function f, which is just the relevant Klein-Gordon operators applied to the Feynman propagator. And let's then evaluate the part of the right-hand side of the LSC formula coming from this term. So we can do so what we need to do is to do the x1 and x3 integrals. And we can do those by changing variables. I'll call x13, x1 plus x3, x13 bar be x1 minus x3, p1 3 to be p1 plus p2, put a half in here, p1 3 bar to be same thing with a minus sign, 3. And we can evaluate the right-hand side of the LSC formula, or this part of it. So what we need to do is take these Fourier transforms, got p1 dot x1 minus p1 dot p3 dot x3 of f. And after this change of variables, we get d for x13, d for x13 bar. We get a half from the Jacobian. We get then e to the I p1 3 bar dot x13 plus p1 3 dot x bar 1 3 f of x bar 1 3. The x bar 1 3 integral just Fourier transforms f. So we get a half integral d4 x13 e to the I b bar 1 3 minus f tilde of p1 3 p1 3 dot x1 3. And this integral, this gives us a delta. So that would give us a delta of p bar 1 3, which we can relate to a delta of p1 minus p3 just by a factor of 2. So we'll have to multiply by a factor of 2 to go from a delta of p1 bar 1 3 to a delta of p1 minus p3. And here we get f tilde of p1 plus p3 over 2. And similarly for the x2 and x4 integrals. So what we see is that the contribution to the scattering from this diagram, so this notation will just mean the contribution from this diagram to the scattering amplitude. Of course, to be consistent, we'd need to add all the diagrams of the same order, but I'm just computing them one at a time. So this is proportional to a delta of P1 minus P3. That's the one we just found. And this is exactly the same argument. Tell us there should be a P2 minus P4 delta. So there's no scattering, which is what we'd expect based on these diagrams. But it's useful to go through this argument and see why that's the case. So we get just the forward momentum of particle 3 is equal to the forward momentum of particle 1. Similarly for 4 and 2. Nothing in this argument depended on the explicit form of our Green's function. All we used really was that this function f was translation invariant. It only depended on x1 minus x3. And that's going to be the case for any disconnected diagram. So any disconnected diagram will have this translation invariance, and therefore we'll have extra deltas compared to what we expect. So we expect the matrix element to be related to the scattering matrix just by one overall momentum conserving delta. Here we've got extra deltas that enforce that one of the final particles is the same as one of the initial particles. And so any disconnected diagram is going to contribute, will have extra deltas. And for 2 to 2 scattering, that means that all of the disconnected diagrams will give us trivial scattering. So this diagram will give trivial scattering where particle 1 just becomes particle, in the initial state just becomes particle 4 in the final state. This diagram is actually a 0. This will have be proportional to a delta of P1 plus P2, which is the argument that that delta will never be 0 because the energies of the initial particles will obviously be positive. So this diagram is just 0. These two are trivial scattering. More generally, if we're considering, say, 2 to 4 scattering, we could have non-trivial disconnected diagrams. For instance, we could have, instead of 2 to 4 scattering where all the particles interact, we could have 2 independent 1 to 2 decays, or just a spectator particle and a 1 to 3 decay. But any disconnected diagram is not really going to contribute to all n particles interacting. And they'll always have extra delta functions, which means there can be no interference between these disconnected diagrams and the fully connected diagrams. So in practice, we can compute them entirely separately. And if we're interested in scattering, computing, say, 2 to 2 scattering, really the only interesting part of the S matrix is the one where everything is connected. So, and usually we just don't consider the disconnected diagrams because they're not interesting. Although they do, in principle, contribute to the S matrix. So if we want to compute the interesting part of the S matrix, then what we have to do is consider fully connected diagrams. Okay, so we need to go to next order, and the lowest, to get a fully connected diagram, and that will give us the lowest order fully connected diagram, which is this diagram. And we can use our position space Feynman rules to write down the expression for this. So we have one vertex, so we get a factor of minus I lambda integral d4y. And then we have propagators from all of our external points to y. So we have a delta 1y, delta 2y, delta 3y, delta 4y. And so this is the first interesting term. And we can do the same thing, try to figure out how this contributes to the S matrix. So to do that, we just note that every time we act with the Klein-Gordon operator on the Feynman propagator, we just get minus I delta. This is the Green's function. And so do we apply all 4 Klein-Gordon operators, these 4 Feynman propagators just become 4 delta functions, which we can use to do the x integrals that show up in the LSD formula. So the contribution to the scattering amplitude from this diagram should be minus I lambda integral d4y. And we can use these deltas to do the x integrals. That just sets all of the x's equal to y. And so what we're left with then is just this e to the I p1 plus p2 minus p3 minus p4 times y. And so we get the expected overall momentum conserving delta. And the matrix element is related to this amplitude by just subtracting off or factoring out the delta. So we get the matrix element is minus I lambda. And so we can draw the same diagram in momentum space. And in momentum space, this diagram looks the same, except we just label it a little bit differently. It has momentum P1 and P2 coming in, momentum P3 and P4 going out, and a single vertex. I'm drawing time going upwards. And I've labeled the momentum of each that's flowing along each leg next to the diagram. So I'm going to reserve lines on the diagram to indicate flow of charge, and I highly suggest you do the same. Okay, so that's our first example for a matrix element. Okay, so let's try to go to the next order. The next order, there's a whole bunch of diagrams. I won't draw them all. But there will be a diagram like this. This is a fully connected diagram. So there will be a diagram like this. And this has two vertices. So it contributes at order lambda squared. And we can use our position space Feynman rules to write down the expression for this. We have minus I lambda squared over 2. There's a symmetry factor of 2 coming from the exchange of the two lines that go from z to z. Exchange of the two ends of the line that go from z to z. Vertices are also associated with integrals over the space-time point. We have integral d4y and d4z. Then we have propagators from 1 to y, from 3 to y, from 4 to y, from 2 to z, from z to z, and also from y to z. Are there any questions at this point? Does everyone see how I went from this diagram to this expression? Okay. So we can try to compute the contribution to the scattering amplitude from this diagram. And, well, the four Klein-Gordon operators, like before, turn these four propagators that involve the external points into delta functions. So we can do the integral over the external points using those delta functions. And what we're left with is this. So e to the p1 minus p3 minus p4 times y e to the I p2 times z. And these two internal propagators don't have Klein-Gordon operators acting on them, so they remain. And to proceed further, we can use our expression for the Feynman propagator. So delta yz is the integral d4k over 2 pi to the fourth I over k squared minus m squared plus I epsilon e to the minus I k dot y minus z. And so we can plug that in there. And then do the y and z integrals. So if we do the y and the z integrals, we get y and z integrals, we get that the contribution scattering amplitude from this diagram is, got our factors of the coupling constants. We have two momentum integrals coming from the two Feynman propagators here. We have the momentum space versions of the Feynman propagators. And then we've got two deltas. So we have one delta from doing the y integral, and the y integral will give us something involving p1, p3, p4, and k. So we'll get something like p1 minus p3 minus p4 plus k minus k. And we'll get another delta coming from the z integral. So for the z integral, the delta z to z will have just a 0 in the exponent, so we don't get anything from there. And so we'll get a p2 plus k. Okay, this is our expression so far. We can use these integrals to get rid of the delta functions. And this last delta function is particularly problematic, because if we just do that part of the integration, the integral of, with this delta function, we also have this Feynman propagator here, got a k squared minus m squared plus I epsilon here. if we do this integral, we set k equal to p2. So this is p2 squared minus m squared, which is, this is a physical particle. It's an external particle, one of the ones we send into our experiment. And so p2 squared is equal to m squared. So this is 1 over 0. This is a problem.
From integrating over z, should it not be like
3
3 terms?
terms? So here we've got delta zz. So it will have a z minus z. So that will cancel.
The last line you wrote, the first delta, is there a minus sign?
A minus.
It's supposed to be minus or plus.
Plus. I
I see that plus.
It should be the same. Signs there just come from the sign here. Yeah. Okay. So this is a problem. We've got 1 over 0, and we need to get rid of this. So the resolution is we need to amputate these diagrams. And we'll discuss more tomorrow in tutorial why we need to do that. But let me just give you some idea of what we're doing and a little bit of motivation for why. So what we need to do is amputate our Feynman diagrams. And what does that mean? So if we've got some Feynman diagram, so we've got a Feynman diagram like this with a bunch of corrections on the external legs. And maybe something crazy going on in between. So this is a Feynman diagram we could draw. It's fairly high order in perturbation theory. But amputation just means, we're imagining here, this is one of our external particles, P1, P3, P4, P2. So this is a diagram that you'd think would contribute to the same 2 to 2 scattering we're considering. Amputation means look at each of the external legs and cut it as far along that leg as you can. Cut it just before it starts to interact with some of the other external particles. So anything that's going on here doesn't involve any of the other particles. If I cut it later, if I follow this line any further, that would affect how it interacts with P4. So if I cut this line here, this line here, this line here, and just replace parts I amputate with a single line, then the diagram takes this form. And so basically, another way of saying that is amputation means we don't allow any corrections to the propagation of the external particles before they meet with some of the other external particles. So this diagram amputated becomes this diagram. And so the part we're discarding, these corrections to the external leg, physically they have the effect of modifying the mass of the particles. So they can change the relationship between the, if we don't renormalize our theory in the way I'm going to describe, they'll change the relationship between the mass parameter that shows up in our Lagrangian and the physical mass of the particle. And we'll discuss that more tomorrow. But once we take care of that, and if we impose the renormalization conditions that I'm going to post tomorrow, then these diagrams are already taken care of. And if we included them when we were computing scattering amplitudes, then we'd be double counting. So we shouldn't do that. And we'll discuss the effect of these diagrams a bit more tomorrow and also in tutorial on Thursday. But you can see that including them causes problems. So for now, we'll just throw them away. And so having gone through those examples, hopefully the Feynman rules that I'm about to write down won't seem like they're pulled out of air. So what we see is that the diagrams that are going to contribute to the matrix element will be the sum of all, or the interesting part of this will be the sum of all completely connected amputated diagrams. And the completely connected is just to look at the part we care about. There are disconnected parts that are not interesting. So those are the diagrams we should consider. And the Feynman rules for going from those diagrams back to an analytic expression for the matrix element are first, for any internal line, we get a factor of I over p squared minus m squared plus I epsilon. That comes from the fact that we'll have a Feynman propagator that won't be killed by a Klein-Gordon operator. And once we write it in momentum space, we'll have this factor. All right. Trivial rule again, for every external line, we get 1. I'm writing this just so you remember when in Tiber's part of the course, when we come to fermions and gauge bosons. For the vertex, in phi-4 theory, we get a factor of minus I lambda. We used these space-time integrations that were in our vertex rule before to do some of the Fourier transforming. So those went away once we wrote everything in momentum space. So it's just a factor minus I lambda. I wrote down an expression for the more general vertex if we have different types of particles, and it's the same thing there. We just have the minus I times the coupling without any space-time integration. Rule 4 is impose momentum conservation at each vertex. So, for example, if we've got in phi cube theory, we have a diagram like this. P1 coming in, P2 coming in, P3 and P4 going out. Then the momentum flowing along this internal line by momentum conservation at this lower vertex, we have P1 and P2 flowing in. So if we have to have P1 plus P2 flowing out. And momentum is automatically conserved at the other vertex because by total for momentum conservation, P1 plus P2 is equal to P3 plus P4. We've got P1 plus P2 flowing in, P3 plus P4 flowing out. Time is going this way. Rule 5 is the same as before. Divide by the symmetry factor. And the last rule is sometimes we don't have enough information to impose momentum conservation at each vertex. And we'll have some undetermined momenta. And any undetermined momenta we need to integrate over. And there'll be one momentum integral per loop. And that can happen if the number of Feynman propagators we have here is not equal to the number of internal points. So there'll be some mismatch. So those are the Feynman rules for matrix elements. And quickly, just see how they all work together. This diagram, we have P1 going in, P3, P4 going out, P2 going in. Momentum conservation at this vertex is not enough to determine the momentum flowing along these lines. But once I specify one of them, suppose I say that there's momentum K flowing this direction, then momentum conservation will tell me that along this other line, we have to have got P2 and K flowing in over here, and P4 flowing out. So we have P2 plus K minus P4. That's how we can use, this is one loop topologically, so there should be one momentum integral. If we write down the matrix element, we've got two vertices. So we have two factors of minus I lambda, the symmetry factor of 2 from exchange of these two lines. Integrate over the undetermined momentum, and we have two internal propagators. So we just write the momentum space Feynman propagator for each of those. And so that's our expression. Using these momentum space Feynman rules. Any questions on that? Yes.
When we do the details above, we have 2 pi over 4 for each delta. So here we don't have to add like some 2 pi's over 4, 2 pi's 4 sometimes.
So our convention is that whenever we have a momentum integral, we've got 2 pi over 4. The 2 pi's to the 4th will always cancel off. We've got factors of 2 pi and our 4 in our momentum integrals, and we'll also get factors of 2 pi to the 4th when we do the x integrals to get delta functions.
So we only put them on the integration.
Only in the integration. So those are the Feynman rules, and you'll explore bit more how to use them in tutorial this afternoon. And then tomorrow, we'll come back to this point that we've been ignoring since we discussed the LSE formula, which is that in order to do perturbation theory consistently, we need to renormalize our theory, or normalize it in the first place. We never properly normalize our theory, and so that will have some interesting consequences that I'll discuss tomorrow. I'll see you at tutorial this afternoon.